Hello and welcome to Chapter 6. We are discussing momentum and impulse. Problem bank number 1 question states that if a blue whale has a mass of 1.46 times 10 to the 5th kilograms and momentum of 9.73 times 10 to the 5th kilograms times meters per second to the south, what is its velocity? We are given our mass of 1.46 times 10 to the 5th kilograms. And we are also given our momentum, which is a lowercase p, of 9.73 times 10 to the 5th kilograms meters per second. Again, here we have a mass and we have a velocity units. So we know that in our formula for momentum, we have mass times velocity, as we will see here in a little bit. Our unknown, or u, is what is its velocity. And we look for our equation, which we just went over. Momentum is equal to mass times velocity. As we substitute in what we are given, we substitute in our momentum, which is 9.73 times 10 to the 5th kilograms times meters per second, and that is equal to our mass, which is 1.46 times 10 to the 5th kilograms, and this is all multiplied by our velocity, or our unknown. In solving this, we're going to divide both sides by 1.46 times 10 to the 5th. We're going to end up with 9.73 times 10 to the 5th kilograms meters. And that's going to be divided by our 1.46 times 10 to the 5th kilograms. This is going to equal our velocity. As we see here, our kilograms will cancel out. We'll only be left with meters per second. And our velocity will be equal to 9.73 times 10 to the 5th divided by 1.46 times 10 to the 5th, or 6.66 meters per second. Moving on to number 3. The current holder of the men's world record for running 200 meters is Michael Johnson, who in 1996 ran 200 meters in 19.32 seconds. Johnson's mass at the time of his world record breaking run was about 77 kilograms. What was the magnitude of his momentum at his average speed? A couple things that come into play here. Anybody that's ever watched the Olympics knows that Michael Johnson did not start running as fast as his top speed, nor did he probably keep his top speed for the whole 200 meters. So what is key here is that we are looking for the momentum at his average speed. Again, looking to guess, we have given our displacement of 200.0 meters. We were given his mass of 77 kilograms, and we were given his time of 19.32 seconds. Our unknown is our lowercase p, or momentum. Knowing that our momentum is a product of our mass times our velocity, we also are not given our velocity, so we will solve for that. From chapter 2, we learned that velocity is equal to displacement over time. And we also know that our momentum is equal to our mass times velocity. Substituting our variables and knowns into our equations, we see that our momentum will equal our mass times our distance ran of 200 meters divided by our time. Substituting in what we know, 77 kilograms times 200 meters divided by 19.32 seconds. We will have our solution. Going to the calculator, 77 times 200 divided by 19.32. Michael Johnson's momentum was equal to 797.1 kilograms meters per second. And comparing that with our first problem and our whale, we see that our momentum of the whale was approximately 97,000 kilograms meters per second. And Michael Johnson running his fastest, or his average speed during a world record breaking sprint was less than 1,000. Something to keep in mind. Number 5, good old Popeye. Popeye of mass 70 kilograms just down a can of spinach. So Popeye is probably just a little bit more than 70 kilograms now, depending on what the spinach weighed. He accelerates quickly and stops Bluto of mass 700 kilograms. So we better use some subscripts here. The mass of Popeye, and we'll say the mass of Bluto. Who is very dense and charging in at 10 meters per second. So we also have a velocity for Bluto. What was Popeye's velocity? So we're assuming that we have Popeye with his big, strong Popeye arms going this way, and we have a much bigger and more dense Bluto coming in this way. And it says that everybody stops. So our final velocity for Popeye and Bluto looks like it's going to be 0. So our unknown is our velocity of Popeye. One equation that we know is that the momentum of Popeye is going to have to be equal to the momentum of Bluto. You know that momentum of Popeye is equal to the mass of Popeye times the velocity of Popeye, and the momentum of Bluto is equal to the mass of Bluto times velocity of Bluto. Substituting in our knowns, let me make sure we understand. Oh, wow. Substituting in our knowns, we see that the mass of Popeye is 70 kilograms. We do not know our velocity of Popeye, but we know the mass of Bluto to be 700 kilograms with a velocity of 10 meters per second. Solving, we see that we will divide the 70 kilograms to get the velocity of Popeye by itself. And as we divide both sides by 70, our 70 kilograms on the left will cancel out, and we're left with the momentum of Bluto divided by the mass of Popeye. We'll see that our kilograms will cancel out. Our 10 will cancel out with 70, and we are left with 700 divided by 7, which is equal to 100. Our only units that are left is meters per second, which we should know is a measurement of velocity, and we are left with a velocity of 100 meters per second. Number 7, we see that Jerome pitches a baseball of mass 0.2 kilograms. So we're given a mass of a baseball. .2 kilograms. The ball arrives at home plate with a speed of 40 meters per second. So we will put our velocity initial at 40 meters per second, and is batted straight back to Jerome with a return speed of 60 meters per second. So V sub F is equal to a negative 60 meters per second, because we have a pitcher and a batter moving this ball in opposite directions. What is the magnitude of change in the ball's momentum? So our unknown is our change in momentum. Our equation to find our change in momentum is going to equal our mass times the quantity of our final velocity subtracted by our initial velocity. As we substitute in our knowns, we see that delta P is going to equal 0.2 kilograms times the quantity of negative 60 minus 40. And these are meters per second. Because these are both meters per second, we can subtract those. So we end up with 0.2 kilograms times a negative 100 meters per second. As we do the arithmetic for that, we see that our change in momentum is going to be equal to 0.2 times negative 100, which would be negative 20 kilograms meters per second. We have negative 20 because our momentum, which started out positive, as we set with our pitcher pitching with a positive velocity towards the plate or the batter, and the batter hitting the ball back with a velocity of negative 60 meters per second. So our change in momentum went from positive to negative. Therefore, we have a negative answer. Chapter 6, problem bank number 9. Lonnie pitches a baseball of mass 0.2 kilograms. It must be in the same league, same size or mass of baseball. The ball arrives at home plate with a speed of 40 meters per second. So our initial velocity, again, is 40 meters per second. And it's batted straight back to Lonnie with a return speed of 60 meters per second. A lot like number 7. If the bat is in contact with the ball for 0.05 seconds, what is the impulse experienced by the ball? So delta T is equal to 0.05 seconds. Our unknown is our impulse, also known again as change in momentum. And we'll be using the same formula that we did before. I guess this is also E. That is our equation. As we substitute in what we know, delta P is equal to our mass, 0.2 times our velocity. And we see that I forgot to put directions on our velocity. Let me go back up there and make sure that's a negative 60. We're going to subtract our 40. And we are just going to end up with the same exact answer for number 9 as we did for number 7. Thank you.